Ever had to schedule a new meeting in a busy calendar and wondered where it fits? Insert interval is a Pattern Mastery 100 staple, loved by Google, Amazon, and Facebook to test your interval merging and array traversal skills. Over 30% of candidates stumble on edge cases, especially when the new event overlaps with many intervals. Master this and you'll breeze through scheduling, merging, and range questions in interviews. Let's solve insert interval using the basic approach, so you can handle any interval insertion or merging scenario step by step. You're given a list of non-overlapping intervals sorted by start time and a new interval. Insert the new interval, merging if necessary, so the output remains non-overlapping and sorted. List of intervals, each as start, end, sorted, non-overlapping new interval, start, end. List of intervals after insertion and merging. Think of adding a new meeting to a packed conference room schedule. You have to insert it in the right spot and merge if there's any overlap. Interviewers might ask, how would you efficiently handle time slot insertions in a shared calendar app? What's tricky? Need to merge if new interval overlaps with any existing. Carefully handle cases where the new interval is before, after, or in between intervals. Avoid unnecessary merges, stick to intervals that actually overlap. Loop through existing intervals. If current interval ends before the new interval starts, add it to output. If current interval starts after new interval ends, add the new interval, then the rest of the intervals, you're done. If there's overlap, merge, update the new interval start to min_cur.start, new.start, end to max_cur.end, new.end. Add any unmerged new interval at the end if needed. Let's clarify. The output must be sorted and non-overlapping. At most one merge run is needed, since input is non-overlapping and sorted. Edge cases. New interval before all others. New interval after all others. New interval overlaps multiple intervals. Initialize an empty result list. Iterate over each interval. If current ends before new starts, append current. If current starts after new ends, append new, then append the rest and return. If overlap, update new interval to merged range. After the loop, add the last new interval if not already added. Return the result. Let's try to implement it using solution 1. Time complexity. O(n) log n. The concept discussion. We're inserting one new interval into a list of intervals, then making sure the final list has no overlaps. This approach is simple. Add the new interval, sort everything by start time, then do a classic merge intervals pass. While scanning, if the current interval doesn't overlap the last merged one, we append it. If it does overlap, we extend the last merged interval's end to cover both. Sorting makes it easy because any overlaps will show up next to each other. This function appends the new interval, sorts by start time, then merges overlaps in one pass. First, we just add the new interval into the existing list. This lets us treat it like any other interval during merging, instead of handling it with special cases. Next we sort by the start value. Once everything is in order, merging becomes straightforward because any interval that overlaps another will appear right next to it. We create a merged array to store the clean, final set of intervals after overlaps are combined. Now we walk through the sorted intervals. There are only two cases. No overlap, if merged is empty, or the current interval starts after the last merged interval ends, we can safely add it as a new block. Overlap. Otherwise, the intervals collide, so we merge them by extending the last merged interval's end to the maximum endpoint. Once we finish the scan, merged contains the final set of intervals with the new interval inserted and all overlaps resolved, so we return it. And that's how this algorithm works. It first inserts the new interval and sorts everything by start time. Then it scans once to either append non-overlapping intervals or merge overlaps by extending the last interval's end. Efficient, simple, and elegant. Let's test our function using this input. We start with these existing intervals, 1, 3, 6, 9, and we want to insert the new interval, 2, 5. Each pair represents a range on a number line, from start to end. This solution takes a straightforward approach. Push the new interval into the list. Sort everything by start time. Do a standard merge interval scan. After inserting and sorting, we effectively have 1, 3, 2, 5, 6, 9. Now we merge. Start with 1, 3, in merged. Next is 2, 5. It overlaps because 2 is within the current end, 3. So we merge them into 1, 5. Next is 6, 9. No overlap this time because 6 is greater than 5, so we add it as a separate interval. And that's exactly what our program outputs, 1, 5, 6, 9, matching the expected result. That output makes perfect sense because 2, 5 overlaps with 1, 3, extending it to 1, 5. while 6,9 stays separate. So, our implementation is correct. The algorithm inserts the interval, sorts once, and merges in a single pass, efficient and accurate. Let's try to implement it using solution 2. Time complexity, ON. The concept discussion. This one-pass approach assumes the intervals are already sorted by start time. Instead of inserting and sorting again, we sweep through the list in 3 clean phases. Add all intervals that end before the new interval starts. These can't overlap, so they go straight into the result. Merge all overlapping intervals with the new interval. We expand the new intervals, start, end, to cover everything that overlaps it. Add the remaining intervals. Once we're past overlaps, everything left also can't overlap the merged interval, so we append them as is. At the end, result is already merged and correctly ordered. This function walks through the intervals once, placing non-overlapping intervals, merging overlaps into the new interval, then appending the rest. We create a result array for the final answer and use an index I to scan through the intervals. Since we're doing one pass, ease our current position through the list. This first loop collects intervals that end before the new interval even starts. Because they're fully to the left, they can't overlap the new interval at all, so we safely push them into result unchanged. Now we prepare to merge. We copy the new interval into start and end because we're going to expand it if we discover overlaps. This loop handles all overlaps. As long as the next interval starts before or at our current end, it overlaps the current merged range. So we widen the merged interval. Start becomes the smallest start we've seen. End becomes the largest end we've seen. When this loop stops, we've absorbed every interval that overlaps the new interval. After merging, we push the final combined interval into the result. At this point, it represents the new interval plus any intervals that collided with it. Now we add the remaining intervals. Because we've already passed the overlap zone, everything left starts after the merged interval ends, so they can be appended directly without extra merging. At the end, result contains the correct interval list with the new interval inserted and merged in the right place. And that's how this algorithm works. It first pushes all intervals that end before the new interval starts, then it expands the new interval by merging every overlapping range, and finally it appends the remaining intervals after the merged block. Efficient, simple, and elegant. Let's test our function with these existing intervals, 1, 2, 3, 5, 6, 7, 8, 10, 12, 16, and we're inserting new interval equals 4, 8. Each interval is a time range, and we want to insert and merge so the final list stays clean and non-overlapping. This solution does it in 3 smooth phases without sorting, because the intervals are already ordered. First, we add all intervals that end before the new interval starts. 1, 2 ends at 2, which is less than 4, so it's safely added to the result. Next comes the merge phase. We start with start equals 4 and end equals 8, and merge every interval that overlaps, meaning its start is less than or equal to end. 3, 5 overlaps. 3 less than or equal to 8, start becomes 3, end becomes 8. 6, 7 overlaps. 6 less than or equal to 8, end stays 8. 8, 10 overlaps 2, 8 less than or equal to 8, end extends to 10. So all of those collapse into one merged interval, 3, 10. Finally, we append any remaining intervals after the merge window. 12, 16 doesn't overlap, so it stays as is. And that's exactly what our program outputs, 1, 2, 3, 10, 12, 16, matching the expected result. The output makes perfect sense because 4, 8 connects and merges the middle block, 3, 5, 6, 7, 8, 10, into a single continuous range, 3, 10, while the outer intervals remain separate. So, our implementation is correct. The algorithm inserts and merges in one linear pass through the intervals, efficient and accurate. Alright, quick recap to wrap up insert interval. We start with intervals that are already sorted and non-overlapping. Our job is to insert one new interval into the correct spot, then merge any overlaps so the final list stays clean, still sorted, still non-overlapping. The main challenge isn't sorting, it's correctly handling overlaps. Every interval we scan will fall into one of 3 situations. It's completely before the new interval, completely after it, or it overlaps somewhere in the middle. Since the input is already sorted, we don't need anything fancy. One pass is enough. And we only merge when boundaries truly collide. The plan is a simple left-to-right sweep. First, add all intervals that end before the new interval starts. Next, while intervals overlap the new range, merge them into the new interval by expanding its boundaries. Then add that merged interval once, and finally append whatever intervals remain on the right. We used a result list and a pointer to scan through the intervals. expanded the new interval during overlaps using the smallest start and largest end, and pushed the merged block exactly once. The solution ran cleanly on LeetCode with no errors. We confirmed it handles overlaps, gaps, and edge insertions correctly. It works when the new interval merges multiple intervals, and it also works when it merges none. And all test cases passed. The takeaway is that sorted input lets you think in clear phases: add left, merge middle, up and right. That structure makes the solution fast, predictable, and easy to reason about, and once you master it, interval problems start feeling much more organized.